he moved to University of Potsdam and did his PhD on the seismic hazard analysis and did lots of data analysis regarding this part. And after PhD, he did his postdoc from UT Zurich. And from that, he joined with us. And from last 1 year, he's with us. And then he's teaching the courses on engineering seismology. And only in this semester, he has started a new course, which is a data analysis using Python. And then number of students here from different departments are then attending these courses. So I invite him again, and then please welcome him for this talk.
Hello. Yeah. Thank you, Professor Jain, for kind introduction. And I can see that the strength is already thinning. I think people are already saturated with the intense course, but it's fine. The good thing is that my talk is in the morning now. So I think in last 2 weeks, you guys have been working mostly on this workshop is about geomorphology, and many of you, as I was told also, that you are working, some of you are working on active tectonics. And as I saw in a couple of talks also, when I was like in the first couple of days, that people were trying to measure slip on some faults. And then we're talking about like this much of slip has occurred in last 100 years or 200 years or maybe kilo years or something like this. So what is it good for actually? And many of you, many of the speakers were referring for seismic hazard also. So today's talk is more like about what is the methodological framework that your active tectonics or those slip measurements of slip is accounted in seismic hazard analysis. So after this talk, so this is more sort of teaching actually. What many, like 70 to 80% content of this talk is what I teach in my seismic hazard course. So by the end of this talk, you will be able to have some conceptual understanding of, I wouldn't say that you will be able to learn, but you will have some sort of understanding that what do we really mean by seismic hazard analysis, right? So because people on and off use the term seismic hazard, that is good for seismic hazard or that is bad for seismic hazard. So you will have some formal understanding of what is seismic hazard analysis, why tectonics and deformation is important from hazard perspective, and how do we account this in seismic hazard analysis, a methodological framework, and how geodetic measurements can be helpful in seismic hazard analysis, like that slip measured on some faults or on faults. So before I proceed, as I said, this will be like more sort of a class. And I request you that it should be more interactive, right? So if you have any questions, you can please feel free to interrupt me. And in between, I will also be throwing some little small questions. So what do you think about seismic hazard analysis? What is your perspective? What do we mean by seismic hazard? Because you must have heard that term, that from hazard, it is this perspective, from hazard that, from higher hazard, lower hazard. What do we mean by seismic hazard? Random ideas, feel free. So I'm not looking for a formal definition, but I'm asking what is your perception of seismic hazard analysis, so, or in general seismic hazard.
If some earthquake occurs,
yeah.
How many number of lives are affected, and what is the loss of property?
Yes.
That comes under, I think, seismic hazard analysis.
Yes, you are somehow a little bit close to that. Any? Yeah.
Almost anything that from flooding situation to tsunami situation, liquefaction. So anything that is related to the seismic wave that can cause any damage to, be it the simple earthquake that damages that is exposed on the surface, there is landslide, etc., etc. So. So more or less everything.
Thank you. Any other idea? Yeah, please feel free, whatever you think about, yeah.
So seismic hazard analysis is actually mapping the damage zones or the potential areas where there are more chances, like if there's a lot of population you have,
yeah.
So it'll cause you more risk. Plus it's also about how the ground is, that place. Another, it talks about recurrence intervals. So
sorry,
how much recurrence intervals, or how much
recurrence intervals? Good.
Yeah, and how much deficit is there?
Yeah.
I mean, you have ongoing conversions. So how much is taken, how much is consumed, and how much is absorbed?
Okay.
So in that way.
Okay. Thank you. So in general, the idea what I get from this discussion is that you are talking about damage or loss of lives, loss of properties, and something like this. But if an earthquake occurs in a region where there is no building, nothing is there, no life is there, do you think hazard will not be there, or hazard will be there?
But we are more concerned about the loss of property. And
Properties,
loss of lives.
Yes. So this is something different that we call risk.
Risk.
Right? That we call risk. Hazard will be there. You cannot reduce hazard. You cannot reduce hazard. Like if an earthquake is occurring, there will be ground shaking because of that. Right? That ground shaking is going to cause damage. Right? So you cannot stop earthquake. So hazard will be there, but you can minimize risk. You can minimize, you can construct your buildings in a way that they will not be damaged. So these are two different things, hazard and risk. So loss of life, the possibility of loss of life, the possibility of a loss of your property or buildings or any infrastructure is risk. But it is coming from the hazard. Sorry. So in general, when we say hazard, we talk about what is the expected shaking at a site. I'm using very generic term shaking at this moment, right? What is the expect? Because if there is an earthquake, there will be shaking. And that shaking is going to cause the damage. Earthquake is itself not going to cause the damage. It is the shaking which is going to cause the damage, right? Are you with me? Any question on this? No? So far so good. Then first is how do we quantify? Because I said we will be talking about formal stuff, what is involved in seismic hazard. So how do we quantify shaking? What are your ideas? So as you can see, if you have a record, any earthquake record, so we can record displacement of the ground, that's shaking. If we can record velocity or acceleration. And we can get either of these quantities by just differentiating or integrating. Like if you have an acceleration record, you can get velocity by integrating it. Or if you have a displacement record, you can get velocity or acceleration by differentiating, right? So the usual way, so these are your just rough idea for different acceleration trace, different earthquake motions. So usually, many of you would have heard in the context of hazard that this much PGA. Have you heard this term, PGA? PGA is right, like peak ground acceleration. So this is the value on either side. It can be a positive or negative. So the absolute maximum of an acceleration trace is PGA. Now the question is, why only PGA? Right? Because in civil engineering applications, when I'm talking about damage and all these things, so seismic hazard has huge application in engineering design. So from the applications perspective, it was thought that PGA means maximum acceleration on the acceleration trace. So that maximum acceleration in some way can be related with maximum force. M is equal to A at the base of any structure. And they found that this is one single number which is convenient to have and which can somehow quantify the severity or the intensity of any shaking. So that's why PGA is like representing the strength of shaking. So we are going to quantify the shaking by, in general terms, by PGA. Now, suppose if there was an earthquake of certain magnitude that produced PGA of 0.45 G. G means 9.8 meters per second square, so you can multiply it with this. And suppose it is this value. So people used to treat this as hazard. That this, when people say that, what is the seismic hazard? People are essentially going to tell you that this is the value of seismic hazard in terms of PGA. 0.5G, 1G, or 2G, or 0.1G. And in fact, in earlier studies, people used to use this value as the value for their design of structures also. So if, for example, there is a largest earthquake in the Gujarat, magnitude 7.6 or 7.7 or 7.3, and that has produced a 0.45G from the past event. So people would say that this is the maximum PGA you can get at this location, so we should design our structure for this. That is called deterministic seismic hazard analysis. There is no uncertainty involved. So that is the maximum earthquake, which, if you have heard this term, maximum credible earthquake, MCE. So the past maximum event is MC, maximum credible earthquake. However, but engineers don't design for past earthquakes. Are they going to design for earthquakes which have occurred in the past? No. They are interested in designing for the earthquakes which will occur in future. This we have to see. They are going to design for earthquakes which are expected to occur in future. So, the rational question an engineer will ask you, what are the chances that this PGA, 0.45G, will be reached or exceeded in next 50 years, 100 years, or 1,000 years? Right? That is how you will design your building then. If someone tells you that there are 90% chances that this PGA in next 50 years is going to exceed or is going to reach, then you will take certain precautionary measures. That out of 100 times, 90 times this is going to exceed. Right? But if someone tells you then only 5% chances or 2% chances, then you will design your building according to that. Those many resources then you are going to put according to that. Right? So formally in hazard, what we call probabilistic seismic hazard analysis, which is the state of the art now, we are essentially treating in terms of probabilities. We are asking how strong, 0.45G, 1G, 2G, how strong is the strength and how much is the probability? Because I also want to know that what are the chances that this is going to exceed or this will be reached. So now a very simple example, that what do we really do in seismic hazard analysis? With a very simple example we are going to understand. And in fact, it is the very simple, thoughtful experiment which is going to tell you how PSHA, probabilistic seismic hazard analysis, is usually done. The basic conceptual understanding. I'm not going to talk about probabilities. Little bit I will talk, but I'm not going to talk about different equations, what are the equations and all these things involved. So for example, if you had a luxury to have a station here at IIT Gandhinagar for last 10,000 years, and you are recording your ground motion. So this time is like last 10,000 years, from today, last 10,000 years. And on this x-axis, you can see P ground acceleration, right? You are recording for last 10,000 years. Now I ask you, because as I said, what is the strength of the shaking? And this strength we are quantifying in terms of P ground acceleration. So now I ask, how many times this PGA will be exceeded, is reached or exceeded per year? Because I'm going to talk about what is the probability that this will be exceeded in next 50 years, 100 years, or 200 years, or 1,000 years. And how we will go there, this we will talk as the talk progresses. So first I want to ask you, how many times this much PGA is reached or exceeded per year? In last 10,000, you have measurements for last 10,000 years. So this is 0.45G. Could you count these instances when it is beyond 0.45G or equal to 0.45G? 8 times, right? So there are 8 times or 8 instances when in last 10,000 years, PGA has gone above 0.45 G. So per year kitna ho gaya? 8 by 10,000, right? So the answer is 8 by 10,000. So I know now that per year, the PGA will exceed 8 10 to the power minus 4 times. So that is what the core concept of hazard. Seismic hazard tells you how strong, 0.45 G, 1 G, 2 G, and how often, 8 times per year. Sorry, 8 10 to the power minus 4 times per year. So we are talking about how strong and how often. So if, see, as I said, this is the entire chain of what you were also saying, that earthquakes are the basic idea of earthquake occurrences comes from plate tectonics. Because of these plate movements, your faults are getting locked or loaded, earthquake rupture occurs, and then we have a shaking at one place. That is what we are interested in. Once you have that shaking, then you tell or you want to know what is exposed to that shaking. Exposed means whether a dam is exposed, whether a simple school is exposed, or a simple building is exposed, or nothing is exposed to this shaking, right? So this is called exposure. What is exposed and what is the vulnerability and what is the situation of that system which is exposed to the hazard? How much vulnerable it is. And then finally, we go to the damage, right? So if we can reduce the vulnerability, like if you have a reinforced concrete cement structure, the vulnerability is little lower. But if you have like those kacha houses made by just mud and stone, you can say that the vulnerability is higher. So that means the damage can be more. So the idea is usually the risk, this is the risk part. And the job of a risk engineer is to reduce risk. I will give you an example if time permits that how people reduce risk. And so you have to keep in mind that in hazard, we are really not interested in earthquakes. We are interested in shaking that is produced by earthquakes. So if someone tells you that the magnitude, there is a large possibility of magnitude 8, which is a magnitude 8 event occurring 1,000 kilometers away from Gandhinagar. So you should not be worried that magnitude 8 is occurring somewhere 1,000 kilometers away. You should be worried what is your shaking, what is the shaking at your location from that earthquake. It's not necessary. If it is magnitude 8, maybe at your location it is 0.1 only. The seismic waves got attenuated, right? So even a smaller earthquake like magnitude 4 or magnitude 5, but quite close to your location, within 50 kilometers, 20 kilometers, can produce significant damage, what a magnitude 8 earthquakes in Himalaya produce here, right? So this was a hypothetical case that if you would be running your instrument at this location for 10,000 years, we could easily compute what would be the expected hazard. But unfortunately, we don't have this luxury. We have at max earthquake recordings for last 100 years, or maybe 150 years, the instrumental records. So what do we do in such case? That you don't have observations for 1,000 years, but you are going to make predictions for next 1,000 years. Even, in fact, for the case of nuclear power plants, for their safety, for their risk assessment, because nuclear power plant is critical facility. If it gets damaged, then many people are gone. So you need a higher level of safety standards for nuclear power plants. So people are making prediction for nuclear power plants and nuclear waste repositories. This is a big, big challenge in at least nuclear waste repositories in Europe and in US. Because the residual fuel, what they are going to put, either they are going to put it in the deep ocean or somewhere in deep, I think as far as I know, there was a problem in Norway and in Scandinavian countries also, that they are putting those nuclear waste materials somewhere deep down. And in fact, if an earthquake occurs there also, even in the case of waste repositories, this is also going to cause a problem. So in case of, for normal structures, we predict for 50 years or 100 years for civil infrastructure. But if you are going to talk about like facilities like nuclear power plants or dams, then you are not talking for 1,000 years. They are now talking for 10,000 years. Because a nuclear material will remain active depending upon its half-life. So it can be there for 10,000 years also. So in that case, we need models. You don't have data, we need models. So certain models we will be talking about. So formally, technically, if you see any presentation or any talk about probabilistic or deterministic seismic hazard analysis, these are some technical terms. You don't have to worry. These are general 4 steps. First is that you try to characterize your source, what type of source it is. In general, earthquakes are caused on faults, but in some cases you don't know, for like smaller magnitude earthquakes, you cannot identify faults also, that at which fault it is, what we call background seismicity. You may not assign a particular earthquake to a particular fault. And then, once you have identified this is your location where you want to evaluate your hazard, and these are all sources. And then it comes activity, recurrence, that how often, this is determined here, how often a magnitude 4, how often a magnitude 5, how often a magnitude 8. This we call source activity. And this is established through Gutenberg-Richter relationship. This we will study in detail. Once you know this, that how often the event is going to occur, then we need to estimate, as I said, we need to estimate ground shaking. You know the magnitude, you know the distance from the source, but still you need to identify this, you need to quantify what level of shaking that earthquake is going to produce. That is done with the help of ground motion models, which relate ground shaking, for example, PGA, to the earthquake magnitude, distance, and some site effects also, site amplification or whatever, but in general, magnitude and distance in earlier time. Then the final outcome is your ground motion parameter, for example, PGA on the x-axis, and on the y-axis, the annual rate, which we were talking, how many times per year. So as you can see, this is called hazard curve. So as you can see, higher the ground motion level, the lesser the frequency. PGA of 1G or 2G will be very rare. PGA of 0.1G will be quite frequent, because magnitude 3 or 4 can also produce this PGA of 0.1 and 1G or 2G. So that's why the lower the ground motion level, the higher the frequency, that it is coming more often. And if it is 1G or 2G, so a lot of calculation is inside this. So I'm just telling you some conceptual ideas that what do we mean by hazard. Strength on this x-axis, and on y-axis, how often. So this is the same thing that we are interested in per year, how many times. A certain, this is rate, lambda, per year, how many times, lambda, that your y, your PGA will be greater than a certain value. So when we talk about rate and probability, so some basic ideas, some basic concepts before we proceed here, because that will be interesting to know first. So like simple examples, if we ask you that how many heads, if you are tossing a coin, how many heads in 500 trials? 500 ट्रायल में कितने हेड? एक हेड आने की प्रोबेबिलिटी कितनी है? एक ट्रायल में कितनी प्रोबेबिलिटी है हेड आने? 1/2. So if I ask you that you repeat this experiment 500 times, so what is the probability of getting head? 500 multiplied by 0.5. Or similarly, in case of a dice throw, what is the probability of that 4 will come in 600 trials? So what basically you do, this is same thing we are talking about. That probability that then in the next die throw, the number will be 4. It is this. Do you know what is the meaning of this vertical bar and then event? I'm talking this in terms of, because this is the formula used in hazard. Slightly complicated one, but do you know what is the meaning of this vertical bar here? This is probability for sure. Probability that y will be equal or greater than y. इसका मतलब क्या होता है? Vertical bar. Conditional. This tells you probability that this y will have a certain value or it will exceed a certain value given, conditional, given that the earthquake has occurred. PGA will not be there unless there is an earthquake. Earthquake has to occur, then only ground shaking will be there. So it is conditioned, right? So this is a conditional probability. We always talk about conditional probabilities. So that's why I'm talking about conditional here, that the earthquake has occurred, then the PGA will be this value. Rate is basically number of trials in your this experiment. So just try to understand it like in a region, how many earthquakes in last 10,000 years? Magnitude greater than 0. These are number of trials. So nature is also throwing a die. 10,000 times it has thrown die. Now you have to identify what is the number in a die throw is like 4, 3, 2 or 1. Same thing, what is the magnitude of that event? Whether it will be 4, whether it is 5, whether it is 6. This is just as simple as to understand it like a die. There were 10,000 trials, right? And now I ask you that in 10,000 trials, what is the probability that this earthquake, an earthquake will get a magnitude 5 or a PGA 1G, right? So what you do, you multiply probability of a single event with the number of trials. So that is what we are doing. These are number of trials per year in this case now. We just divided it by the time. Per year. Per year, those many trials. And then we just multiply with probability of one event. So the question in seismic hazard analysis, again I emphasize, just to, and I write this to show you some similarity with our die experiment or tossing a coin, that how many events over a chosen time period, because then we can divide by the time period to get the rate, and what is the probability that earthquake will have a certain magnitude m or it will generate a PGA 1G or more. That is what we are interested in hazard. Now, because we are talking about frequency, that means we are talking about recurrences. How many, how often? So how do you establish the recurrences? How do you? What is needed to get the annual frequency or the recurrence of a particular event, that how often that magnitude earthquake is occurring in time? What do you do usually? Or what would you do? Your ideas. What would you do?
So we date an earthquake event, and we record so many earthquakes, number of earthquakes.
Yes.
And then we find the recurrence interval.
Yes. Yes, you are quite close to that. So we basically make a catalog of earthquakes available in time. whatever date we have, like from last 1600, 1500 or 1000 years also. We try to make a catalog in terms of their magnitude on one side, on one column, and on the other side, that when those earthquakes occur, 1961, 1650, 2001, 2002, so we mention their time also. Because we are talking about making predictions in time, annual frequency. Annual means yearly rate we are talking about. Once we have this catalog, and if you plot on the x-axis earthquake magnitude, basically magnitude and number histogram. I'm talking you just plot a magnitude histogram. How often, like magnitude 4.5, in your catalog it is 100 times. Magnitude 4.5 to 5, there are like 50 times. So you plot those histograms. So, but we will see this histogram. You need records, all sort of observations. As I said, instrumental records are very, very limited. Even not for 100 years, as I was telling you. Then you go for historical seismicity. This we call, one is instrumental seismicity, that is recorded by the instruments. Then historical seismicity, which is around for which goes like around for 1000 years. So this historical seismicity, you know, many people are doing paleoseismological studies. We will come to that also. Archaeoseismicity and all these things. We try to get the data from wherever possible. And that was, I think in Europe even, and unfortunately it is not the case in India, but in Europe and in some other countries, particularly in Europe, they have mentioned about those historical earthquakes in some notes or in some books in churches also. And many people are still working on historical seismicity. So they are just going to check the old notes, very like 500-600 years old, whether they are available in some churches or some villages or somewhere. 700-800, they are trying to look for those historical events also. So this is a different field of research, historical seismicity, and archaeoseismicity and paleoseismicity, you all know. I don't know. Okay. So it's slightly slow. It took. So let it come. So then once you have those catalog of earthquakes, that on one axis I told you the time, and then you plot you have earthquake magnitudes. Oh. Out of memory. Out of memory कैसे चला गया भाई? So I will open it in preview, not in Acrobat. So this catalog of earthquakes, you can use data from, in case of instrumental data, there are many websites like ISC, Cosmos, and different other organizations. They are trying to collect just the earthquake data, the epicenter, magnitude, time of occurrence. And this is very important part of any sort of seismic hazard analysis study. So as I was talking, in terms of historical seismicity, if you go, in Italy it is like they have data, at least they can go up to 1,000 years, in France 1,000 years, Switzerland 700 years, China 3,000 years. So they have some documented proof for some earthquakes in China also. US around 200 years, and in New Zealand around 150 years or something. And with the catalog is always there is a problem that different magnitude scales, right? You know, there are different magnitude scale, local Richter magnitude scale, moment magnitude scales. You know these magnitudes. So often the magnitude scale which is reported in the newspaper, which magnitude scale it is? Richter, right? But people are using more in seismology the MW. So different organizations who are maintaining a network, they often report ML or Richter magnitude scale. But then you have to homogenize your magnitude scales. You have to bring them in one magnitude scale, whether it is ML or MW or whatever it is. Then if you plot your number of earthquakes on the axis, the magnitude of earthquakes on the x-axis, like magnitude 4, 5, 6, 7, and here number of earthquakes per year. So in 10,000 years, you calculate total number of earthquakes, magnitude 4, between 4 to 4.5 or magnitude 4.5, and then divide it by just that time interval, and then if you plot, then you will get this sort of relation. So this is values incremental, and this is the cumulative one. Cumulative means number of earthquakes greater than magnitude 4. Number of earthquakes greater than magnitude 4.5. So this we call incremental. So interestingly, the distribution what it follows, on the y-axis you see the log. So what kind of distribution it follows? Exponential distribution, right? So from here you can get an idea from Gutenberg-Richter relationship that what will be the annual rate that this earthquake or an earthquake will have a magnitude 8. Can you get it from here or not? Because this is giving an annual rate for different earthquakes. So that is where we get, if you have the earthquake data, keep in mind. So this is basically the formulation, that number of earthquakes log A minus B, where B is magnitude. So A and B values are determined mostly from regression, from the data. So that is what we call seismicity analysis. One interesting thing, because there was some discussion coming about seismic gaps, right? Seismic gap everyone knows, that the fault got logged or something in last 200 years, that this magnitude is not occurring, and there's supposed to be a magnitude 8, but it has not occurred in last 200 years. The question is, you see this is a very famous relationship between earthquake energy and magnitude, MW. There are different relations for surface wave magnitude, energy wave magnitude, but I'm talking about MW, moment magnitude. So you see from here that if an earthquake has a certain magnitude, this will be the associated energy release. Now if you have a magnitude 5 and magnitude 6, I ask you what would be, how large the energy release of magnitude 6 in comparison to energy release of magnitude 5. That is around 32 times from this relationship, right? So agar, if I can produce, if you say, someone says that magnitude 8 earthquake is bound to come there, but if I can produce 7 magnitude 7 earthquake, 32 magnitude 7 earthquake, so I'm compensating for this total energy. Like magnitude 8 will produce certain amount of energy. That energy I can match by just producing magnitude 7 earthquake, but 32. Are you getting me what I'm saying? So 30, magnitude 4 to 8 will, 4 to 6 variation will be 32 multiplied 32, almost around 1,000 times. So if I can produce 1,000 smaller magnitude earthquakes, but accounting for the same energy release. So it's not necessary that your energy release or your total moment is released by the large earthquake only. That total moment release can occur by smaller earthquakes also. So this is an example. This is just showing you this. On this axis, you see magnitudes, and here the energy release. So number of smaller earthquakes are more. Like per year, you get at least 100,000 earthquakes overall across the globe. But as I said, as the magnitude increases, the number of earthquakes also increase. So magnitude 8, 9, or 10 are very rare. But as I said, you can account for this variation in energy by just number. So this was about recurrence, that how often is certain event is going to occur. Now is like how do we model our sources? The best way is that we model our source by a fault, because often earthquakes are occurring on the faults. At least larger earthquakes of magnitude 5 or 6 are occurring on some identified faults. So one way is that we model our faults. But in general, magnitude less than 5.5 or magnitude 6, they are not on fault. So people, or you don't have well-identified faults. First, you should have faults also. You should know. In those cases, people usually characterize these sources in different source zones, like they make some polygons, and they assume, and for each polygon, they have this catalog of earthquakes, and from them, then they use this Gutenberg-Richter relationship to get the annual rate of accidents for each source zone. So the assumption is that in each source zone, the seismicity is same. From that analysis, you can get the annual rate of accidents. So this is the concept for seismic source zones, but the question of your interest is coming now. If you don't have a catalog of earthquakes, what do you do? If you have, then well and good. If you don't have, but you have a well-identified fault, you know the dimensions of the fault, you know the depth of the fault, you know the length and width of the fault, you know the strike of the fault, and luckily now you have a GPS measurements and you know what is the average amount of slip occurring every year. So I'm taking some examples from Europe, because mostly I have been working before in Europe, and I have just started working in India. So you see these are mapped active faults. And this is the reference where I got it from. In California, at least many of you know that most of the large earthquakes in California are associated with the San Andreas fault system, right? And in fact, we will see some examples from there. So first is, because you all are geologists, so could you tell me what is an active fault? Displacement required to be active. Good, yeah.
Fault line along which there is measurable
movement. Is there something, because we are always talking about time. Yes.
11,700 years.
11,700, it's in India. Yes. Okay. So I took some examples in USA. So they say that at least one movement in the last 50,000 years. In Japan, evidence of movement in the Quaternary time. In China, evidence of at least one movement after late Pleistocene. I don't know what is the time associated with Pleistocene. But for many critical facilities activities within the Quaternary in last 1.6 million years or this, there should be at least some movement around or on this fault. Now, you guys are good in this, right? Mapping faults. Anyone has some experience with the active fault mapping? So have you done something? Field measurements? Where?
So we're doing measurements along the frontal thrust of the Himalaya.
In the frontal thrust?
Yes, sir.
HFT or?
HFT.
HFT, okay. So you are going on the fields, right? Okay. So I will just be going through them, because these are not my research area. Fault mapping I'm not doing, at least till now I'm not doing. So these are some pictures which I took from my colleagues. So you can see that one way is mapping is faults is that you go to the field and you see some fault scarp and all these things. Another way is that dam. Many people are using here dam, right? Your geomorphological studies. You see any change in river profile or something like this, right? These are also some proxies to identify faults. Now people are also using LIDAR, at least in California. In India also, I think they have started using LIDAR or not. No? Anyone knows? No. So this is very high precision because this gives you high precision digital elevation maps. And the good thing with the LIDAR that which is not available with the DEM, that it can even work in case of vegetation. INSAR data. People are using this also, this difference in phase, like for example, for this case. So these are just some techniques. Now, once you have identified your fault system, then what is the slip? How do you constrain the slip? This is one thing. So how do you usually constrain? If you have now GPS measurements, right? You can tell what is the average slip rate. For example, with this 10 to 25 millimeters per year, Indian plate is moving under thrusting the Eurasian plate. Or paleoseismological studies. They can also tell with time that this discontinuity in different sedimentary layers, they can also tell what was amount of slip around that particular event. So basically, we are interested in identifying earthquakes, when did they occur, and what was the amount of slip one earthquake is going to produce. Why? I will come to that. So basically, we are building a chronology also in terms of paleoseismology, that this is your time, number of earthquakes, when this earthquake came, when this earthquake came. So these are uncertainties in time, because in paleoseismology, you cannot tell exact time that this came on that day. And in fact, paleoseismological studies, you can use different segments of the faults to identify the slip on different segments on the fault. Like in case of in San Andreas systems, so when they identified the locations of paleo events, they identified what was the amount of slip by that event, and then they went to the next location, then they went to the next location. So they could eventually identify the total rupture. If the fault breaks in one go, what would be the total expected rupture length and width? This is from San Andreas, from California. So the basic idea, as I said again, that you have fault models, you need spatial geometry, you need deformation on those faults, slips, what amount of slip has been produced. Then you can get this slip to moment, because we are interested in magnitude, energy. Then you can convert the slip rates to moment rates. Moment rate will be basically magnitude rate, we will see. And then we generate the probabilities model. So for example, if you know from your slip measurements, your GPS tells you a certain amount of 15 mm per year, right? That this is the slip rate on a certain fault in last 10 years. How do I get the earthquake it is going to produce? How do I convert this slip rate to an earthquake magnitude? Any ideas? Any one of you have seen this relationship where M0 is seismic moment, mu is the modulus of rigidity, A is the area of the fault, D is the displacement. This is seismic moment, right? Displacement. If I take this derivative of this M0, what I will get? Moment rate. Mu and A remain like this, d by dt. What is this now? Displacement rate, basically your slip rate, right? So that is how, and this dm0 by dt basically becoming mu as, where s is your slip rate, and you know I can convert this m0 to mw using the Hanks-Kanamori's relation. M0 can be associated with the mw, seismic moment. That's why it is called moment magnitude, right? Because mw, moment magnitude, is associated with the seismic moment. This is very famous relationship. But whatever slip rate you have, and from that slip rate you are getting moment rate, right? how this moment rate release is distributed in terms of magnitude and in terms of time, because that's what we are interested in, is strength and how often. One way is that whatever slip, total slip in last 10 years has accumulated on a particular fault, one can say that this total slip can get released in terms of moment only in one event. This is one possibility. Yes or not? This is one idea, no? That you have total accumulated slip of 10 meters. For example, in last 100 years. From 15 mm per year, you compute it for last 100 years. So what, it will be around 15 centimeters or something. So if there is a 15 centimeters of total slip accumulated, that means you can distribute that slip in moment now. One possibility is that there are small portions of magnitude which are accounting for the 15 centimeter slip, or one is that you generate a single earthquake which is responsible for a 15 centimeter slip. So, yeah.
Can you say a little bit about moment? What does it mean by moment?
Seismic moment.
Yeah.
So, you mean how do we estimate it, or?
No, simple, what is the meaning of moment?
Yes, so moment is force into displacement basically. Right? That is what moment is, right? So moment, seismic moment is basically that what is the fault dimension you have, and then the amount of, like before the earthquake your faults are logged like this. Then suddenly they got ruptured. So the amount of displacement that has occurred from its original position, that you measure, right? And from this, if you multiply, there is some formulation that how you, I can't recall that formulation, but it basically comes from force into displacement. It's the same unit, force into displacement. So the total amount of moment that is released. So this is the displacement, right? But the formulation is coming from the force into displacement basically. So if I say that the total slip that has accumulated can get released in one event. So now I should know what is the magnitude of that event. So I should convert that total slip back to moment. That I can do. And the question is, on average, how often that earthquake will occur? Because we are interested in what will be the strength and how often. So if you know the length of the fault, you know the width of the fault, and this is the slip rate you have. From the length and width, I can calculate an area of the fault. And area of the fault is related, there is an empirical relationship which is by Hanks and Bora that you can, Hanks and Bacon 2008, where you can relate the fault of an area with the magnitude. So if I assume that this total length and width is going to rupture in one event, or total slip is going to rupture in one event over the entire fault, what will be my magnitude? So this is my magnitude, 7.2. And this is the empirical relationship between A and magnitude, area and magnitude. So that is how you can compute magnitude. Now, yeah.
Is also valid for the Himalayas?
Yeah, this is a global earthquake. It is a global earthquake. People are using this. Now, I know what will be the magnitude. Because I can compute, you have a slip rate. From slip rate, I can compute magnitudes. M0. From M0, I can compute magnitude. Now, the question is, how often in the sense? I know that 7.2, 15 centimeter slip or 15 mm per year slip can produce a magnitude 7.2. Now, the question, how often? So, for that, if the slip rate is constant, that it is not varying in terms of time, which is a very huge assumption in itself. Because in some years, your slip can be large, in some year, your slip can be small, but we are talking about average slip rate. So the number annual rate of earthquakes I can get if it is my moment rate that is coming from the slip rate, and if it is my moment of one event, I can get how many events per year. Just dividing your total moment rate by the moment of one event. Moment of one event I know now. Magnitude 7.2. I can convert it into moment. So I can tell what is the characteristic, what is the annual rate of that event. So basically there are some distribution of, this is called characteristic magnitude, that, and this is still used in many countries, that the earthquake after a certain interval, this will repeat this magnitude earthquake. This is called characteristic magnitude. And a return period is associated with this, that every 200 years that earthquake will be repeated. So this is called characteristic, and in some countries it is still followed. So this is the distribution, because it will always, you can assume that it is uniform distribution, that it has averaged the same probability of occurring 7.2, or you can ascribe it a normal distribution, that some years it will be 7.2, some years it will be 7.3, or some years it will be 7.1 sometime. This is one possibility. This is frequency magnitude distribution, which we were talking in the beginning. But people have seen that some faults are generating earthquakes according to Gutenberg-Richter relationship. That there are larger number of smaller earthquakes and a smaller number of larger earthquakes. That exponential distribution. If you put this exponential distribution in the denominator, because here we put only just single number, only one earthquake, we are saying that every time in every 200 years, the same magnitude earthquake is repeating. If you describe the annual rate of occurrence of earthquakes according to this distribution, so you just put this distribution here, and you can get how many earthquakes beyond that magnitude or of that magnitude you can compute. So this is annual rate. That is how you are computing here. From the slip, you see, from the slip we went to the moment rate, from the moment rate we went to the number of earthquakes per year, because your slip is per year, your moment rate is per year, so we can compute how many earthquakes per year. Now I said in the beginning, what we will do with this per year business, that what will be the PGA annual rate of PGA occurring more than 0.45 G, how many times per year. This will be used to make prediction in time, that in next 50 years, next 100 years, next 1,000 years. This is done with the help of Poisson's distribution. Poisson's distribution tells that occurrence of earthquakes in time is independent. Like, that means if an earthquake occurs of certain magnitude occurs today, the probability of occurring that same magnitude of earthquake tomorrow is same, after 5 days is same, after 10 days is same. So in terms of intervals, that if an earthquake is occurring today, it does not affect the probability of occurring the earthquake tomorrow or the day after tomorrow. It does not affect. So it's a memoryless system. So here you will put this rate, lambda, which we were computing, lambda here. And here T is the time interval for which you are going to make predictions. So this will give you the probability that what will be your probability that PGA 0.45 G will be exceeded or PGA 1 G will be exceeded in next 50 years or 100 years. This you can get from here. But is this the case in reality on the faults? ये केस तो नहीं है. अगर एक मैग्नीट्यूड 7 का अर्थक्वेक किसी फॉल्ट पर आज आ गया, तो फॉर श्योर प्रोबेबिलिटी कम हो गई उसके आने की, सेम मैग्नीट्यूड अर्थक्वेक आने की अगले एटलीस्ट एक हफ्ते तक.
But in Japan, this Poisson model.
Poisson model.
Yes.
Why do you think so?
Because every time you are having a lot of earthquakes, not exactly like in the Himalayas. In the Himalayas, if you have a 8 magnitude or 7 magnitude, then you will reduce the probability of having another 7 magnitude.
Yes.
But in case of Japan, you are sitting on a ring of fire, the subduction zone. So over there, you are having a lot of every year or 7, sometimes 6, 7 again and again. But in case of Himalaya, we do not have. So there are a couple of papers they talk about. So you can model the Poisson model earthquakes from the Japan, but
in
not
time,
from the Himalaya.
Yeah. Okay. So in general, because we don't, yeah, please.
So it's two plates versus a number of plates together, which is what will happen in Japan. If you have a triple plate junction or further,
Yeah.
then you have a greater probability of earthquakes, because if one plate moves, it will affect the others.
But you think that if there is an earthquake on a certain place today, or we are talking about like in faults, if there is an earthquake today occurring on a particular fault, do you think that the probability of same earthquake is reduced or is same, is not reduced by occurrence today?
No, it is reduced, but it is reduced to a far more extent possibly in the Himalayas than in Japan.
Yes, yes. That can be. But in general, if we go to the basics, elastic rebound says otherwise. The Reed's hypothesis, it tells you that if fault has ruptured today, that your fault is getting locked over time and then it suddenly ruptures, and then most of the stress that is stored or strain energy that is stored, it is released. Now it will take some time to build up again. So that is what we call earthquake cycle hypothesis, right? So Poisson's model does not account for this. Poisson model says that if the earthquake has occurred today, it doesn't matter whether it is occurred today or tomorrow, your probability is going to remain same. But this Reed's hypothesis says otherwise. If the earthquake, most of the energy that has released, the probability of occurring the same magnitude earthquake tomorrow is slightly lower. After some certain interval of time, it can increase again. But in near future, it has reduced. So in accounting for this, people are trying to account for this also. One is from the catalog, again, because from the catalog, we got only mean rate, average rate. We did not look the inter-event time. What was the distribution of time interval between two events? We did not look this. If you have sufficient information, you have enough data that you can have this distribution of inter-event times. What is the time between two events? And you can generate a histogram. So that histogram will give you the mean as well as standard deviation. And if you have the distribution, then you can make the probabilities also. So this is a statistical way of doing this. And people have started doing this. But as I said, there is no sufficient information even to account for time dependency, even from the well-identified faults also. But this term is now has started what people call time-dependent seismic hazard analysis. So how to include faults in seismic hazard analysis? This is a big effort going in California. This, I took some papers, some examples I took from here, and you can see that this is, they have released third uniform earthquake rupture forecast. So they are associating probabilities from the slip, they are going to the rupture seismic moment rate. From the moment rate, they are associating probabilities for different earthquakes also. This is happening in California. This is the recent paper that is released in 2014, I guess. And then similar efforts are in Europe also. Fault to PSHA, fault to SHA. How do you link those slip rates, whatever data you are getting from your geodetic measurements, to seismic hazard analysis? A big effort, a big group of seismologists is also working in this in Europe. This group is called Fault to SHA. So that's all from my side, just to give you an idea that how whatever you are doing, how it is relevant in the context of seismic hazard analysis. Thank you for your patience. So if you have any questions.
So sir, you talk a lot about slip rates.
Yes. Yeah.
How are seismologists looking at modeling this liquefaction? Because that's a huge issue in alluvial plain areas, I would presume.
Liquefaction, I would say that is more from civil engineering, geotechnical aspects. People are trying to look on this. So from seismological perspective, we don't try to model liquefaction. Yeah.
But not even how depths of sediments can influence slip rates. So for example, if it's not in a hard rock area, say, because I come from there, say from the Ganges Delta.
Yeah.
We have, I presume, a hinge zone. And a lot of the worries there is about what would happen to if liquefaction occurs to a city like Calcutta. So are there any models or measurements of that?
No, that I'm aware of, no. Yeah. Yeah, I think Bodo has some.
I was wondering about the seismic moment. I'm familiar with the way how you define it, and I'm always wondering how well can you constrain the slip area, and what is the best method to get an idea of what is the area that is actually slipping, because that's what you're multiplying by,
yes,
right? By
yes,
times the A,
Yes, yeah.
You can easily get the surface throw by field mapping and other measurements, but determining the exact depth and area that is being ruptured, is that only done through seismic analysis?
Yes, mostly from the field measurements, I would say.
Yeah?
Yeah. Because from signals or data processing, I don't think that we can get moment. We can get moment from the records also.
Yeah.
But it is total moment we can get, but we cannot get the amount of slip or area from the records itself. But moment we can obtain from the record itself.
Okay.
Yeah.
So what I understood is that using slip rate, we can able to reach a conclusion about how many number of earthquake can occur in future.
Yes, yes.
I guess in that model they might be using some equation. I'm just trying to understand, trying to know. There are some earthquake which do not show any slip rate.
Good question. Yes.
So in those model, is there any component where they used those earthquakes which did not produce any displacement?
Yes. Yes.
So those model, did they incorporate that issue, or is there any way to incorporate those things?
No, as far as I know, these models are not accounting for this. Like they believe that whatever slip has accumulated or slip rate is there, it is going to get released seismically, not aseismically. So this is the basic assumption there. So that's why it may sometime overestimate hazard or particularly overestimate in that case. But I don't think that they are accounting for this, that this slip which has accumulated over the years can also get released as seismically.
So, is there a way to incorporate those things in other way, like theoretically or in other way? Is there a way to do that, or is there any studies like that?
No.
Not yet.
I don't think so.
Okay. Thank you.
Yes, any other question? Yes.
Thanks, sir. Sir, I want to ask about when we define seismic gap. So we are defining seismic gap when, in case of we do not have earthquake records, or we are not able to measure through GPS and other geological methods. So when we say seismic gap, so how to say this area is under seismic gap?
Yeah, it's quite debatable now actually, because I thought that seismic gap they say in terms of like a characteristic magnitude.
Okay.
That this region is supposed to produce, or this part of a fault is supposed to produce that magnitude over a regular interval of time, right? But as I said, in hazard we are really not interested how regular that release of energy is occurring.
Okay.
It may get released aseismically, or it may get released the same amount of energy which has accumulated over the years in terms of slip, may get released in smaller earthquakes also.
Okay.
So it is not necessary that that earthquake will get repeated over the same interval of time. So it's not necessary. So even smaller earthquakes can also release that amount of energy which you are expecting.
Okay. Thank you.
Any other question?
Is there a way to understand the aseismic component of a seismic event? Like, I don't know.
As far as I think, an earthquake is always associated with a certain amount of displacement. That's how it is earthquake. But the slip is How the creep mechanism, I don't know. Like if you are talking about that, this slow movement, people have started recording slow earthquakes also actually, which are lasting for days or months also.
Okay.
So this they have started recording, at least in the Cascadia, Western Canada, in these regions. But in terms of methods, I'm really not aware that how they calculate or how they are measuring this thing, or how do they measure this seismic thing. But they have started recording what they call slow earthquakes.
Okay.
Yeah.
Any other questions?
No. Okay, then thank you.
So we can take a 15-20 minutes break. Tea is served outside. After that, we'll have one more session by Bodo.